Hi everyone. In this supplemental screencast, we're going to talk about the Coriolis effect and how it relates to global climate. By the end, you should be able to define the Coriolis effect and describe its effect on prevailing wind and ocean currents. And finally, you should be able to describe the consequences of the Coriolis effect for global climate and specifically how it relates to Kanza Prairie. As the Earth receives energy from the sun, most of that energy is received near the equator, or it's received at the highest energy density. We talked about photon flux density. That's measured in the amount of incoming light energy from the sun. And what you're seeing here is net radiation. This is the difference between the incoming radiation from the sun and the outgoing radiation of the Earth. So the Earth is warm, it's radiating heat back into space, and the difference between that input and output is what we call the net radiation. Now, this imbalance where you see high net radiation near the equator and low net radiation near the poles sets up a differential, and air masses move from the warm equatorial regions, they rise, and then they move north and south towards the cooler polar regions. So that energy differential sets up what we call a heat engine, basically moving warm air masses to cooler areas. On a small scale, we can see this kind of movement of warm and cool air masses along coastlines. So the phenomenon of sea breeze is a result of the shoreline, land near the shore, warming more quickly than water does. So if you got this nice warm land, the air over it is also warmed, and warm air creates an area of low pressure, and the warm air rises. As it does this, new cool air comes rushing in from off the water to replace this rising warm air, and that creates the feeling of a sea breeze all day long. Out here over the ocean, the air is relatively cooler, and it descends to replace this replace the sea breeze air that's moving inward, moving landward, and this creates sort of a daily sort of cell of air movement. At nighttime, the reverse is true. Land cools faster than water because water has a higher specific heat or a higher heat capacity. So once you get late into the night, the land is relatively cool, the air descends in an area of low pressure, and the warmed water, the water that's been warming all day, radiates some of that heat slowly back into the air. So that creates an area of relatively warm air, and the warm air rises. So the cell is reversed. These patterns are sort of analogous to the Hadley, Ferrel, and polar cells that we talked about in lecture. So now let's relate those Hadley, Ferrel, and polar cells to the Coriolis effect. Let's start by just giving you a definition. The Coriolis effect is the deflection of wind and water currents as they travel very long distances across the Earth. And this deflection happens because of the rotation of the Earth. Basically, as we talked about in class, surface winds traveling north or south are deflected to the right if they're in the northern hemisphere, and surface winds in the southern hemisphere are always deflected to the left. We'll talk about why that is, why that's right and left. And in the back of your mind, I want you to be thinking about how the Coriolis effect might relate to climate at Kanza. So why the deflection? Well, the short answer is because of the conservation of angular momentum. The Earth is about 40,000 kilometers in circumference, right? That's the length of the equator once around the Earth. And it takes nearly 24 hours for one complete rotation. So any object that's on the surface of the Earth at the equator has to travel about 40,000 kilometers in 24 hours. What does that come out to in kilometers per hour? If you do the math, you get something like 1,670 kilometers per hour. It's not exactly 24 hours in a day, it's a little bit less than that. And of course, 40,000 kilometers is an estimate. So depending on exactly which numbers you use, you'll get slightly different answers, but basically about 1,600 kilometers per hour, or 1,700. Now, at the poles, and at sort of zero, at 90 degrees north latitude or 90 degrees south latitude, this is Antarctica down here, so 90 degrees south latitude, and the object on the surface there would be basically standing still, rotating, but standing still. So you've got, in addition to this heat engine that we talked about, there's also a major difference in the speed of objects at the surface of the Earth. If you imagine that we're looking down at the surface of the Earth from the North Pole, so this dot in the middle represents the North Pole, and the Earth is rotating. Imagine that these dotted lines represent 30 degrees north and 60 degrees north. Anything that's out here near the equator is moving very fast, right? Nearly 1,700 kilometers per hour. Anything in the middle is barely moving, and then you've got velocities in the middle at mid-latitudes. So if you have an object that's at about 30 degrees north latitude, say a descending mass of air could be your object, and it's moving south towards the equator, the further south it goes, the faster the land underneath it is moving. So the path of that sort of relatively slower moving air as it moves south is deflected to the right. That's a consequence of the Coriolis effect. The wind is, in a sense, kind of falling behind the surface of the Earth as it moves south. This region between about 30 degrees north and the equator is the region where we talk about the trade winds. And the trade winds are in the direction they are in the Atlantic from Europe across North Africa and then over along the equatorial region of the Atlantic as a consequence of moving south. By contrast, if you're at about 30 degrees north and you're a descending mass of air and you start to move north, the land underneath you is going slower and slower as you go north because the distance of a single point on the surface of the Earth up here is much shorter than a point that travels this distance. So as you move north, you're again deflected to the right because you're sort of moving faster than the land underneath you the further north you go. This pattern, where we go deflected to the right by sort of northward traveling air masses between 30 degrees north and 60 degrees north, is what we call the Westerlies. This is what it looks like in 3 dimensions on the surface of the Earth. About 30 to 30 south, you have the trade winds. These are winds that are moving north or south towards the equator and are thus falling behind, deflected to the right. These are the surface winds of the Hadley cells, descending cool, dry air that moves towards the equator where it warms and picks up moisture and ultimately rises to create that intertropical convergence zone in a region of low pressure. The Westerlies are the surface wind portion of the Ferrel cells in the northern hemisphere and in the southern hemisphere. These patterns of surface winds are also what helps to drive surface ocean currents. So notice the pattern of the blue Westerlies, the yellow and the brown trade winds, and compare that with the ocean currents you see here. This is the North Atlantic gyre. It's a rotation, it's the movement of water currents around the surface of the Atlantic in the northern hemisphere. Notice that the Gulf Stream starts down here near the equator, near the tropics, where the water has been warmed for quite some time. And as the warm water moves northward and then eastward across the Atlantic, it's bringing that warm tropical water first to the coast of North America, and then at about Cape Cod, it cuts east across the Atlantic and delivers that those warm currents to the Iberian Peninsula, to Ireland and England, and to Norway. So it keeps Europe rather warm compared to Quebec or northern Canada at the equivalent latitudes on the other side. As the heat is released, the finely cooled water moves south along the Canary Current, along the coast of Africa, until it gets close to the equator, where you get the equatorial current. So this is the North Atlantic gyre, and it's set up in part by winds creating ocean currents. And you can see other gyres, the South Atlantic gyre, the South Pacific gyre, the North Pacific gyre. These are all rotating in the direction they are and delivering heat in the way that they are because of the Coriolis effect. One of the consequences of this is the distribution of Mediterranean climates around the world. Mediterranean climates are winter wet and summer dry, and they occur at mid-latitudes on the western edge of continents all around the world. You can see them in North America and South America, in Europe and Africa, in Australia, and even in Southern Africa. The warm, dry climates of summertime and Mediterranean climates results in vegetation that's specialized for those conditions. And one of the consequences of that is vegetation that's adapted to high fire risk. So plants not only can tolerate burning, but in some cases require burning to complete their life cycle. So you can see that the patterns of ocean current movement and the pattern of wind current movements have effect on climate, and climate has effect on vegetation and the biology of organisms. So why are they on the western edge of continents and mid-latitudes? Well, basically it's because during the, let me go back here. Basically it's because they are along these cool currents. Notice we've got a cool ocean current here, cool Peru ocean current, a cool current along the coast of Africa in the north and in the south, and a cool current along the west coast of Australia. These cool currents and cool air masses that are over them don't carry a lot of moisture. So in the summertime, they're not getting as much rain as they would otherwise if they were somewhere else. So notice the coast of the southeast of the United States or the Pacific Northwest. Those are places where there's a lot more moisture coming off of the ocean, and you have wetter climates, not Mediterranean climates. So this is what a Walter-Leith climate diagram looks like for Mediterranean climate. Notice that during the winter months, in this case in California's northern hemisphere, there's a surplus of water, but then during the summer months, there's a deficit of water. This is what leads to the dry adaptations of plants, or the adaptations of plants to dry environments, and in many cases to fire. So how does all this relate to Kanza? Well, at about 39 degrees north latitude, right here in Manhattan, Kansas, we're squarely in the Westerlies. So the prevailing winds are from the west to the east. Obviously that varies with weather patterns, but the prevailing pattern is from the west to the east, and any air masses that are coming in that direction have been over the continent for quite a while and have lost most of their moisture. So you're effectively in kind of a rain shadow, a long-term rain shadow from the Rocky Mountains. Now there is a source of warm, moist air that could bring precipitation down here in the Gulf of Mexico, but remember, any warm, moist air moving north, in this case, would be deflected to the right, to the east. And that's why you see this sort of southeastern section is the area with the highest precipitation. Now, I want to make it clear that even though we talked about these boundaries, the equator, the 30 degrees north latitude, 60 degrees north latitude as boundaries between the Hadley, Ferrel, and polar cells, these are dynamic boundaries. And you can trace those dynamic boundaries by looking for the subtropical jet stream and the polar jet stream. So this is a cartoon showing just how those can fluctuate And during the summer months in the northern hemisphere, Kanza is mostly between the subtropical and the polar jet stream. So notice that means the westerly winds that are coming sort of up from the southwest, the prevailing westerly winds, are going to be bringing some of that warm air from further south. But then in the wintertime, we might transition to being in the polar cell, one of these lobes of the jet stream. The polar jet stream could dip far enough south that we're up here in the cool air masses, and that's where we get those really cold winters. The last thing I'll say is that we talked about the continental climate, Kanza Prairie. Notice that here in Manhattan, Kansas, we're right in the middle of the continent. Of course, Mexico and Canada are not shown. But at the very beginning, I told you that water has a high heat capacity and land has a much lower heat capacity. That explains why coastal areas, whether they're near a cold current or a warm current, tend to have a more moderated climate. Their winters aren't as cold and their summers aren't as hot. Whereas in the center of a continent where you don't have that moderating effect of the ocean, you can get really hot summers and really cold winters. Okay, that's the Coriolis effect. Be sure you know how the sort of global heat engine and rotation of the Earth sets up these deflection patterns that move moisture and heat around the Earth in characteristic ways.